Here we go. So we definitely want pictures, right? Gotta sketch these. When it comes to basic functions, you gotta know how to sketch those without your TI. Hopefully you're getting practice at this. Things like easy parabolas, square root, e to the x, ln of x, lines, of course. All these things you should be able to, or in Calc 2, you should be able to sketch those without too much difficulty. So 2 radical x looks like this. Y equals x looks like this. And now we want to rotate that thing about the line x equals 5. So we really need to know, where does x equals 5, where does it land relative to that intersection point? So we know we're going to have to find that, so let's just go ahead and find that. So that is where we can set the y's equal, and so that point is going to be where x equals 2 radical x, or x squared equals 4x. And that's going to be x equals 4. Okay, so x equals 5 then is going to be out here to the right of that. So I'll just get rid of this part of those graphs. Knowing that the curve is the y equals 2 radical x, y equals x. So there's x equals 5. And so the intent was to use washers. So are we going to get washers from horizontal strips or vertical strips? And that's a question you should be able to answer. So when I use vertical strips, what will I get? When I use horizontal strips, what will my elements be? So I want washers. What should I use? Horizontal strips will give me washers. Okay, so there's a horizontal strip. So let's, I actually forgot to draw the region. So the region, so that point there is going to reflect about here. And then when this thing has rotated 180 degrees, something like that. And so what will this thing look like? It'll have a hole in the top, right? There'll be open space there. And then on the outside it'll be rounded. And then it'll be sort of like this. And then from there we'll have straight lines. So this thing I'm drawing is mostly space, right? It's mostly space. Where's the actual solid part? It's just like, it's like a shell, right? It's like a conical shell with a curved outside. So all this stuff is space, right? And our actual solid is it's like a conical shell-like thing with a curved outside. It's kind of like a funnel. It's kind of like a funnel. It's upside down there. Okay, and so when we rotate, we know that when we rotate that thing, we're gonna get we'll get our washer. So our washer will look like horizontal. Okay, so there's our washer, and we're going to do we want the volume of the typical washer. So delta meaning a little bit of, right? A little bit of volume. That's our element, so a little bit of volume element. And so we know a volume of washer is going to be pi r outer squared. H minus pi r inner squared h. So what is h is the easy part? Is that delta y or delta x? That's going to be delta y. So all that's left is the outer and inner radius, okay? So the outer radius, so that's going to be from the center of rotation to the outer, and you've got to use the original region. You can't use this. I can't come over here and find that outer radius by looking at this mirror reflection. I've got to use the original region when I'm doing these radii. So I need that dimension right there. So is it an x, a y, a change in x, or a change in y? Is that distance an x, a y, a change in x, or a change in y? You should see that that's a change in x, so we're going to have x2 minus x1. And our x2, this first one, is always what? It's the one further to the right, because that's going to be a greater value. We want a positive radius, always a positive. These distances are always positive. So x2 will be the one further to the right. So that will be, what is x2? Always 5, right? It's that center of rotation. Okay, so we're going to have five, okay, minus x1. So what is x1? x1 is this right here. So it's the x-coordinate of that point. And so which equation is that from? This one, y equals, that's the curve, right? Y equals square root of 2x. And since we're going to have delta y, we do need to rewrite that. So sometimes when you set up these things like the change in x or change in y, hopefully we'll see an example of this. So we would start off by saying like 5 minus x, okay, squared. Sometimes you end up just leaving it x because I guess this happens in shells mostly. In shells this will happen. If we were doing delta x, then we'd be done, right? You're not going to rewrite it. You just would have 5 minus x. But since we have delta y, we have to rewrite that in terms of y. So you don't always rewrite it, is what I'm saying. It's whatever you do to match it to whatever delta you have, either delta y or delta x. So if you always start by asking, is it a change in x, change in y, x or y, you'll save yourself from always rearranging these formulas when you don't need to. Okay, so always start by saying change in x, change in y. So this is a change in x. So it's 5 minus x, and then if this were delta x, we'd be done. Do you see? But it's not. It's delta y, so we do have to solve for x. So what is x? Y over 2 squared. Let's solve this for x. So I got y over 2 equals square root of x. So x is y over 2 squared. So I can come in here and change that to y over 2 squared. And so we got that's the whole pancake without the hole, right? And now we got the second one, which is the inner radius. The inner radius is from, I'll do it in blue. Inner radius is from here to here. X, y, change in x, change in y. Change in x can be 5 minus x, where x is now this equation, right? So it's going to be the y version of this x, which is just y. So that one's easy. So this is going to be pi times 5 minus y squared delta y. And I think we got it. So there's our setup work. There's our volume of our typical washer. Right, so all the washers have that volume dependent on what y is, right? So when y changes, you get different volumes of different washers. Starting at which one? So y equals 0. Okay, y equals 0 is it has the biggest hole and the least amount of stuff, right? And then all the way up to, is this 4? Yeah. All the way from 0 to 4. So now our volume of this thing is from 0 to 4. Pi times 5 minus, can I do y squared over 4 for simplicity there? Squared minus pi times 5 minus y squared all times dy. Okay, questions? Did I lose you? So now that we've dug into this, you worked at these, it should today in class it should come together. Everything should come together. What questions do you have on that one? Anything? Are we good? So, there is appropriate and inappropriate use of technology. Okay? This would be appropriate use of technology. You could put this in this. I know that if you worked hard enough and did all the algebra right, you could get this number. But because that's pretty awful, you could use Wolfram Alpha on something like this. And just get the number, make sure you have enough decimal places, and then do that. Okay? So there's appropriate and inappropriate use of Wolfram Alpha. If it's an easy one on the test, often on the test I'll just ask you to set them up first and foremost. But I won't ask you. Sometimes I'll ask you to do the antiderivative and solve it, but it probably won't be this intensive. Okay. So yeah, everyone should know how to do that by hand. Okay. But this, that when you make a couple mistakes, this could cost a half an hour, 45 minutes of your life, right? So use Wolfram Alpha. Okay. Any questions? All right, next one. Number 6. Good. We got one over y equals -4. Nice example. Okay. So this one, we got make a good sketch. X equals 4, x equals 9. Y equals 1 over x squared. Again, something you should be able to sketch. Just like that. And then we're going to go from 4 to 9. And then, and y equals 0. What is y equals 0? Make sure you don't say that's the y-axis, that's the x-axis, right? All points that have a y-coordinate of 0 is the x-axis. So then we get this initial region like this. This is y equals 1 over x squared from 4 to 9. And we're going to rotate this about y equals -4. Okay, what will it look like? This is pretty easy to visualize what this will look like. So our mirror image or our 180-degree image over here will be something like this. So then what do we get? Maybe easy to visualize, maybe a little tougher to draw. Okay, so let's try to do it here. So we're going to have, on this side, we're going to have a big hole like that. That'll be the right-hand side. And then it'll sweep out like this, and then that. And then there'll be a straight hole right through the middle of it, right? Straight like that, and then there'll be a hole down here. Something like that. It's like a roll of toilet paper that got wet, right? It got wet on the left side and it flared out. Whatever works, right? Okay, so here we go. So we want washers. Washers, is it going to be horizontal strips or vertical strips? So if we did horizontal strips, we would get, should see that we would get shells, right? But look at the disadvantage to that, because here's our height of our shell down here, but then what happens? Up here we have a different shell to create. So if you were to do shells with this, you'd have two different typical shells, right? The one that goes from 4 to 9, first of all, and then the one that goes from 4 to the curve as they move their way out. So definitely to your advantage here to use to use the washers and do your vertical strip. So we'll do a vertical strip here. All right, here we go. So we'll have our, let's draw it in here. Whoa. So there's our pancake, our washer, I mean. There's our typical washer in there, and it's volume again, so a little bit of volume here, and that's of a washer. And we're going to pi r outer squared, h, minus pi r inner squared, h. Outer radius. So that's from the center of rotation to the outside of our pancake, from there to there. X, Y, change in X, change in Y. Is that just an X coordinate, a Y coordinate, or a change in X or a change in Y? That's a change in Y. Do you see that? That's a change in Y. So it's going to be Y2 minus Y1. We just have to figure out what Y2 is and what Y1 is. Yeah?
Is it true to say that instead of having two different volumes, can you just have pi and then as the radius, the outer radius minus the inner radius and then that quantity squared?
Yeah, so you want to factor out the pi and the h?
Yeah.
Absolutely. Yeah. So if you want to work on it this way, pi times, so you want to look at it that way? It's the same thing. Yeah, you're just factoring out pi. It's perfectly fine. Sure. Okay, so we got our change in y. What is y2? The curve, right? The y2 is that curve, and are we gonna? Is our h going to be delta x or delta y? We're going to have delta x for h. So let's just start by writing it as y2 minus, and then what is y1? Negative 4. So minus negative 4 squared, and then minus pi. Inner radius is going to be, I'll do that in blue. Inner radius will be from here to here. And that's our inner radius, our inner. So that one's, you should recognize that's just really easy. What is that? For all of the washers, do you see that that inner radius is 4? So you could do 0 minus negative 4, fine. Because 0 is the outer, sorry, it's the inner radius, is 0, and then to negative 4. Or you could just recognize, oh, that's just a distance of 4 for the whole way. So this one is going to be, what? 4 squared delta x. So all we have left now is to change this y2 into terms of x, and that was this curve right here. So that, what is that? 1 over x squared. So just change that to 1 over x squared. Okay, so two ways of looking at this. So that outer radius you can think of as y2 minus y1, and you get the 1 over x squared minus negative 4. Or you can just say, hey, look, it's just this y coordinate. It's just this y coordinate here plus 4. So that outer radius is just the y coordinate, and then minus negative 4 ends up being just plus 4. And you just see that from the beginning. Oh, I'm just going to add 4 to that y coordinate. Either way, gives you the same thing. Okay, and then we're going to, so we have delta x, so we have to, where's the first washer? Here, that's the biggest washer down here on the left. Is that x equals? 4. Smallest washer on the right. So this is really easy because they gave it from 4 to 9, so we're ready to go now. So this volume of the TP equals integral 4 to 9 of this thing. So pi times, can I fit? 1 over x squared plus 4, quantity squared, minus 16 pi dx. Made it. Okay, now that one would be very appropriate to do by hand. That's not bad. And then before, and so when you multiply this thing out first, look for combining like terms before taking your antiderivative, so you have less antiderivatives to do, right? So you'll get 16 pi there. Look at that, you get 16 pi and then minus 16 pi. And so that would make things very nice, right? So you just lose that term completely. Okay, questions on this example? Okay, let's do one from the first shells assignment. Last chance, gonna erase it. Last chance. All right, let's look at the shells assignment. What was that? 12? 13? Okay, looks like number 3. Okay, so this one, y equals x squared, y equals 0, x equals 1, x equals 2. So definitely a very easy thing to sketch. Should all be able to do this. Y equals x squared, x equals 1, x equals 2, about x equals 4. Okay, so there's a great advantage to shells over washers here. It's the same one we saw last time. If you do washers, so in the last one, it was a great advantage to do washers over shells, because with shells you had two different typical shells to make. Here the opposite is true. If you do it by way of washers, you've got 2 different washers and 2 different integrals for washers. But shells, there's just one typical shell, so one integral.
I just have a question. If you ask us to draw a graph on like a test, and you have something like x squared, do you want us to draw the whole x squared, or can we just draw what's
well, certainly if it matters.
Okay.
Yeah, but just to be sure, draw the whole thing, unlike what I just did, right? Yeah. So, but if this over here mattered, then it definitely would be wrong. But just to be sure, yes, sketch the whole thing. So yeah, I did not do that. You caught me. All right. So here's this thing. So our shells, if we rotate about this region about x equals 4, are we going to get shells by horizontal strips or vertical strips? They're saying vertical. Agree with that? Vertical shells give us strips. Okay, vertical shells give us strips. Okay, and we're going to go by 4, so we're going to get this thing reproduced over here, like when we hit. When it hits 180 degrees, it'll look something like that. And so we'll get something similar to the last one. That was like a bell. That's right. So then this would be that. Is that right? I think that's right. So that's what we're going to be looking at here. And so our shell then will look like this. Draw it inside here. Super thin. Okay. So there's our typical shell, and we know that the little bit of volume of a shell is length times width times height. So it's going to be 2 pi r times height times width. And what's our width here? So, so width is this little dimension here, which is? They want delta x, that's right. Okay, so when we say the height of a shell, we'll always mean this distance, like if it was a can, it's always the distance from like the bottom of the can to the top of the can, no matter how it's oriented. So if it's lying on its side, we'll still call the height that dimension from disk to disk. Does that make sense? We'll always call that height the dimension from the bottom disk to the top disk, no matter how this thing is, whether it's standing upright or on its side. So this is the height. What is the height? X, y, change in x or change in y? Just a y coordinate, right? Just y coordinate. So that's y. Radius. Radius is from outside of the shell to the center of rotation. But again, you've got to use the original region. Don't use your reflected or your rotated region. So x, y, change in x or change in y? Change in x, right? So it's going to be like an x2 minus x1. What's x2? Rightmost x? 4. Leftmost x is? X of this curve. X of this curve. So it's just 4 minus x. X referring to this curve right there. Okay? So what do we need to change? All we need to change is the y. So notice this by saying, oh, it's just a change in x, and starting off by writing 4 minus x, we're done. Okay? You're not going to solve that for y because we are in it's in terms of x here, delta x. So 2 pi 4 minus x stays as it is. And what is y? This y coordinate of this curve is x squared. Okay, ready to write the volume? So the volume of the bell with a hole in the top is going to be from, so now our last shell is this one out here. This is easy, right? So the outermost shell is, you're going to, in your original region, you're going to look at x from the left to the right. Okay, so that the leftmost x value is the outermost shell, the shortest one. And then all the way to the innermost shell on the right, and that's the tallest one. So 1 to 2, 2 pi, 4 minus x, x squared, dx. Super easy integral. It would be faster to do it by hand than with Wolfram alpha. Typing that thing in would take longer than actually solving it.
Pull the 2 pi out front, right?
Sure, any constants. But the only thing about that is when you pull the 2 pi out in front, now your integrand is no longer a volume. See? So it's the same, you get the same answer, but now what you're taking the integral of is no longer a little volume. It's something else. We don't know. That's the advantage to keeping the 2 pi in there. Now I'm looking at, what am I looking at here? I am looking at the volume of a super thin shell, right? That's still a volume. That's a dV now, dV of shell. Okay, other questions? Yes, sir?
Yeah, so this is probably super simple, but I kind of missed it. So why is it 4 minus x?
Okay, because do you see that this is the radius of the shell?
Yeah, sure.
And do you see that it's a change in x?
Yeah, so 4 minus.
So you could be the rightmost x, which is 4, minus the leftmost x, which is the x coordinate of this point on this curve.
Right.
And since we're not changing this, we are in delta x. We're not going to rewrite it in terms of y because it's delta x. So we're done. 4 minus x. Not convinced.
I don't know. I'm still confused.
You're used to always taking that x and solving for y. Is that what you said?
I think so.
Yeah. So that's why I'm training you guys to do this question. Is it x, y, change in x, or change in y? Because sometimes it'll just be, in this case, it's just a change in x, 4 minus x, and we want it in terms of x. So it's 4 minus x. It's the x coordinate of this point right here. So for the very first shell, x is 1. For the very last shell, x is 2. And then all the x values in between.
I think maybe in the beginning I had some confusion too, like as x begins to move between 1 and 2,
Yeah,
you can take off any number between 1 and 2.
Yep.
See, so at any point the radius is going to be between 1 and 2.
That's right. We have all the shells starting at the widest shell, the greatest radius, which is going to be 4 minus 1, all the way to the smallest radius, which is going to be 4 minus 2. And then all the ones in between will be determined by 4 minus whatever the x-coordinate is between 1 and 2. Have a sandwich and think about it later. It'll work, yeah.
Would it be safe to say that whenever you say you have the original region to the left of the axis of rotation, the radius will be a change between two coordinates, whether it's x2 minus
So, okay, so maybe, but so where you're going with that is there, because can I memorize something? And so there's so many different cases and scenarios that just don't try to memorize these little rules. It won't help. Really just do each one case by case. That's going to be your best way to approach that. So yeah, maybe you got some rules like that, but I wouldn't try to come up with little things to memorize because I think it'll be more a hindrance than a help. Other questions? Yeah.
Is there an example where both the shell and the washer method result in having to get two different typical shells?
Mm-hmm. And that would be, that'd be a little fiendish. Yeah. So yes, we could come up with one like that, but typically you don't have those examples. Yeah. But yeah, so definitely. But you'd have a more complicated region to start with.
Sure.
Yeah. So let's have you work on one example. Last chance for questions on this. So for Friday, you'll have another shell set. Okay? And whenever you want to, so if you want to think of it as washers and set it up as washers or pancakes also, it's great practice. Well, let's do one more example. You guys work on it.
Are you always going to give us the method that we're supposed to use?
No.
No?
So I want to do this last one here. Set up the integral to find. And if time, let's see if we can do it two different ways, right? So, but let's practice shells since we've done a little bit less of that. So you figure out what is it going to be a vertical strip or horizontal strip? They're going to create shells in this case. And then if we have time, we'll do the other, whatever the pancakes or washers turns out to be. I'm going to change it to, let's do y equals 2. Definitely a region we should be able to do without a grapher. And you're going to choose strips to make shells first. Make sure you figure out which strips will make shells and do it that way first. Do they think it is?
I don't think so.
It's okay if they do.
I just.
It's there, but it goes just like no, you're right.
What? Set it up.
If thoughts can't exist, my thoughts can't exist, therefore I can't think because thoughts don't exist, therefore I don't exist.
So I have
See, I'm using the logical fallacy and everything must think for me, and so not that thinking.
Okay, so your radius, you should have gotten 2 minus y for your radius. So first of all, horizontal strips. The radius is 2 minus a change in y, 2 minus y. And that just stays, right? That just stays because we're doing delta y. The height down here, the height is a change in x. Final x is 1. Initial x is the x coordinate of the curve, which we have to solve for because we're doing delta y. So x is y to the 1/3. So we got 2 pi, 2 minus y, 1 minus y to the 1/3. dy, and that's y goes from. So in our original region is how we get the boundary. So to get the limits of integration, you go to the original region. Y goes from 0 to 1. Questions? If you need, you could do this one with washers and recitation if you need more time. Maybe something else for you. That's shells for that one. Ask me on the way out if you got a question. So one web work could be more shells for Friday.